All right, this is section 5.2, verifying trig identities. What I look at this section and what I say is this is essentially, most of the questions are proofs, which means I give you a beginning and you have to prove to me that it equals to the end. And you'll see, before we get to the proofs, I have some tips that you should write. You don't have to copy these down word for word, but maybe into some shorthand. Stuff you've heard me say before. It is not a good idea to try to do something to both sides of the equation. Rarely have I seen it work. Can it be done? Occasionally, but I would say students in the past have been much more successful if you just focus on either the left-hand side or the right-hand side. And the one that I would say to work on first is the more complicated side. All right, because if it's complicated, it's going to be easy to simplify. Instead of trying to take something that's relatively simplified and make it more complicated, that's that's usually much trickier. So the steps that I would be looking to do, if you think about last section, what did we learn to do? We learned to factor using trig identities. We looked at a lot of them. We added fractions using trig identities. All right. Some of the techniques you'll see today, you'll be doing some squaring, but a very important one is multiplying by the conjugate. So conjugates, remember something like if I give you ax plus b, its conjugate would be ax minus b. And the nice part about those is that was really easy to multiply because it would just be something like a squared x squared minus b squared. Remember the conjugates, the center terms in the trinomial always canceled out. Use those identities from page 340. All right, keep those handy all section long. Those are you have to use them, whether it's a Pythagorean identity, a reciprocal identity, conjugate identities. They're all there. Not conjugate identities, but either way. A new strategy, similar to number 2, is if nothing's working, you can try writing everything in terms of sine and cosine. Sometimes that works, not all the time, but it's a strategy that we will use. And the other idea is it's a puzzle. No one ever solves a puzzle the first time, so sometimes you just got to start over. You might go down a wrong path, and hey, it happens. I do it too. There's no one way you have to solve this. There's many times more than one, and you just need to find one of those many paths, and it's not always obvious. So it takes a little bit of practice. So don't give up. All right. So we are here trying to verify that sine squared minus 1 over sine squared is the same. Secant squared minus 1 over secant squared is the same as sine squared. So I look and I see all these squares, and I think there is there's a Pythagorean identity I could use here. 1 plus tangent squared is equal to secant squared. Right, that's one of our Pythagorean identities, and I could use that right on the top. I could actually simplify this piece out. Another way to do it, so there's two ways. Actually, if I take my identity and I subtract 1 to both sides, I know that tangent squared theta is equal to secant squared theta minus 1. So now I actually know what my entire top is equal to. All right, instead of writing secant squared minus 1, I can write the entire top as tangent squared theta over secant squared theta. All right, so I've simplified a little bit, but still I haven't gotten down to just a sine theta. So I think about tangent, and I go, well, there's another way to write tangent. My reciprocal identities. Not reciprocal. What are they called? Quotient identities. Your quotient identities. Sine squared theta over cosine squared theta. That's the entire top. The bottom, well, secant, by the reciprocal identities, I could write it as 1 over cosine squared theta. All right, this looks like a complex fraction, but complex fractions aren't usually, there's an easy way to deal with them. If you know that you are dividing two fractions, well, the same as dividing by a fraction is the same as multiplying by a reciprocal. So what you think about, sine squared theta over cosine squared theta, we already know this is a division. But I'm not worried about the division problem. I'm going to say, you know what, it's a lot easier to multiply by the reciprocal. And if I multiply by the reciprocal, well, Now cosine theta is on top. There's a 1 on the bottom. And now I see a cosine squared on the bottom and a cosine squared on top, and they cancel, leaving me with the sine squared theta. And I know I am done because it matches what I've looked at the beginning. By no means am I saying you're going to find that path on the first try, but you now have strategies of looking to use your Pythagorean identities. You know to write things in terms of sine and cosine. You've simplified using some complex fractions. Those are all techniques you could use in the future. All right. Here, again, most of the problems in this section are going to be verify, or if you want to think of it as prove. We're looking here, I see two fractions with two different denominators. And I think, well, to be able to, and they're telling me to add them in the middle, well, to be able to add them, I'm going to need a common denominator. So to get a common denominator, and again, I'm not even worrying about the 2 secant squared. We'll hope we end up there. What I want to worry about is how can I get common denominators? I multiply the first by 1 plus sine theta over 1 plus sine theta. That'll get the bottom the bottom denominator is the same. And here, I need to multiply by 1 minus sine theta over 1 minus sine theta. Again, you need common denominators to be able to add fractions. So this distributive property is relatively straightforward. It's still 1 plus sine theta. The bottom, I could FOIL, and it would be a little bit, because it's a conjugate, and I know it's so easy to multiply, I could write the bottom as 1 minus sine squared theta. And I get that because I see there's two conjugates here and here are conjugates, so they're easy to multiply. Again, a straightforward distributive property, 1 minus sine theta over the bottom, again, 1 minus sine squared theta. All right. Resist the urge to try to cancel anything out yet because we haven't added our fractions together. Now I know we're going to have one denominator. It's going to be 1 minus sine squared theta. And I look at the top, I'm going to be adding. And I say 1 plus 1, that's 2. And the sine theta and the negative sine theta, they've canceled out. So I have further simplified. Of course, I'm looking to get to 2 secant squared theta, and I'm not quite there yet. So I think, all right, 1 minus sine theta. I see a 1 and I see a sine squared, and I think, you know what? That's 2 of the pieces that I need in my sine squared plus cosine squared equals 1. That's 2 of the 3 pieces. So if I just think and I say, you know what? This is my Pythagorean identity. I know that's not the only, that's the way I remember it, but I know there's other ways to write it. Right here, we can see that cosine squared theta is the same as 1 minus sine squared theta. So keep the top as 2. 1 minus sine squared theta is the same as cosine squared theta. So we're doing a lot of substitution today. But there's replacing the 1 minus sine squared with cosine. All right, we're almost there. A cosine in the bottom of a fraction, well, if I move it to the top, it's the reciprocal identities. That's the same as secant squared theta. That's using our reciprocal identities. Okay, here, another proof. We're going to try to prove that tangent squared x plus 1 times the quantity cosine squared x minus 1 is equal to negative tangent squared. Ooh, looks like a tough one. But I think back, and right off the bat, I'm thinking, tangent squared theta and a 1, that looks like a Pythagorean identity. And in fact, it's verbatim. My tangent, this right here, this whole piece, is equal to secant squared theta. So, right, that whole piece is equal to secant squared, they use x here, so secant squared x. So I look, well, this piece has the cosine part. It's got the 1 part, it's missing the sine part. So going back to the sine squared plus cosine squared equals 1. If I subtract out this to both sides, well, now I have sine squared is equal to 1 minus cosine squared. Not quite what I have. If you notice the way I've written this, sine squared x is equal to 1 minus cosine squared x. There's a couple ways you could deal with this. You could look at your identity and say, I'm going to multiply both sides by -1, or you could factor out -1 from here. So it's a little bit tricky. I like the factoring out portion. Like if I take this, to be able to match this, what's in this blue oval, to that, I need to factor out a -1. And if I do that, factor out, -1, leaves you with negative cosine squared x plus 1. And now everything I've written in red matches up with sine squared x. So I could copy this over one more time. Secant squared x times -1. So I'm just going to put a negative sign in front of the whole statement because this is all just one term. Instead of writing negative cosine squared x plus 1, I'm going to write times sine squared x. So I've simplified, but I clearly haven't simplified enough. And I look at secant squared, that can be written as 1 over cosine. So if I think, oh, there's my negative sign, 1 over cosine squared times sine squared. You think, all right, well, the top of this fraction is equal to sine squared. The bottom is equal to cosine squared. And I know sine over cosine is tangent. So again, the negative from the very beginning copies over. And it's tangent squared x because the whole top is equal to sine. The whole bottom is equal to cosine. Sorry, I made a little mistake here. Going to erase everything and start this over. So I look here, and what I say when I'm looking to solve this, I think this left-hand side is a little more complicated because there's that addition in there. And I do know tangent can be written as sine x over cosine x. And I do know that cotangent can be written as cosine x over sine x. So far so good. There's plus in the middle. And what I'm looking to do is try to get common denominators. To get common denominators, I'm going to need to multiply this by sine x over sine x. And I'm going to need to multiply here by cosine x over cosine x. So this is going to get me that nice common denominator of sine x cosine x. And this denominator is the same, sine x cosine x. So then I'll be able to add them. I can simplify the top. Sine x times sine x is sine squared. And cosine times cosine is cosine squared. All right, so far so good. If I try to write that as just one fraction, the whole top reads sine squared x plus cosine squared x over sine x cosine x. And I hope the top is screaming at you. The top should be screaming at you Pythagorean identity. That entire top, we have seen it enough now. Sine squared plus cosine squared is just 1. The bottom is still sine x cosine x. And here's where it kind of, now you need to start paying attention to how do I get it to look like this? Well, 1 over cosine is the same as secant. 1 over sine is the same as cosecant. So you would say, all right, this is equal to secant x cosecant x. Be finished.